This is the next video in a series of videos about catalysis. In this video, we're going to connect kinetics, which we've been talking about for many videos, back to equilibrium and show how we've secretly been using it the entire time. So, kinetics and equilibrium are actually related. So the reaction rate, which is part of kinetics, and the equilibrium constant, which is part of equilibrium, obviously, we're connected all along. Let me show you how they're connected. We'll do it for a nice, simple, generic reaction. A goes to B. So we, now that we've learned about kinetics, know how to write the rate law for this reaction. So the rate law for the forward reaction equals rate constant K, and we'll call it K forward since it's part of the same step, times the concentration of the reactants, A. And we can also write the rate law for the reverse reaction, like we did in the very first video in this chapter, the reverse rate. So we'll call this K, K reverse, and we'll draw it down here on the bottom side of the equilibrium arrow. The reverse K times the concentration of the reverse reaction reactants, which are the products in the forward reaction. Okay, so we can write the rate law for each direction. And then if we want to relate it to the language of equilibrium, what do we know about equilibrium? We know that at equilibrium, the rates of the forward and the reverse reaction are the same. Remember that from the very first video in the equilibrium chapter, we talked about how we didn't necessarily know if the concentrations of reactants and products would be equal, but we knew that the rate of the forward and reverse reaction would be equal. This is because equilibrium is related to rate. It's related to kinetics. So let's use that. So if we know that the two rates are equal, let's set these two rate laws equal to each other. So we'll say rate forward equals rate reverse. So we can plug in K forward times A equals K reverse times B. That was a substitute. And now let's rearrange those, because we're trying to connect the rates with the equilibrium constant. And we know the equilibrium constant looks like products over reactants, right? That's where we're going here. So if we want to write an expression for products over reactants, we want that expression to look like B over A for this reaction. And if we want to rearrange this to get B over A, that means that we need to divide both sides by A, and we'll divide both sides by K reverse. So we'll have K forward over K reverse, and that equals concentration of B over concentration of A. And that means this is equal to equilibrium constant big K. So what we hid from you in the equilibrium chapter was the reason we used big K to represent the equilibrium constant is because it's really made up of lots of small k's. The small k for the forward and the small k for the reverse reaction. So that big K equilibrium constant is simply a ratio of the small k values. And that's where that equilibrium constant comes from. We can see that if the forward reaction happens more than the reverse reaction and products are favored, this number is going to be larger over this number, which is smaller. You'll have a K value greater than 1. And if we have something that's reactant favored, where the reverse reaction dominates, or mostly reactant favored, then that means the reverse rate constant will be larger, the K forward will be smaller, and we'll have a number that's less than 1. So everything we know about equilibrium comes from the rate constants for those two processes. And now that we know about K equilibrium and how it's related to kinetics, we can connect it back to catalysts. So remember what we said about catalysts when we first introduced them? They increase the rate of the forward and reverse reactions. So what would that look like in the rate constant? We specifically said a couple of videos ago, we said that it affects the kinetics, the reaction rate, but it doesn't change the equilibrium constant. So if it affects the K forward and K reverse, how can it not affect the equilibrium constant? Let's take a closer look. Here we are. So we said, when we drew this reaction diagram, we said that the kinetics of the forward and the reverse reactions are improved by that catalyst. We decrease the forward activation energy and we decrease the reverse activation energy. So that means not only are we speeding up the forward reaction, but we're speeding up the reverse reaction, and we're speeding them up in the same amount. So that means that even with the catalyst, the value for K remains the same. As long as we increase the numerator and the denominator by the same amount, we don't change the actual value for the ratio. So that's why adding a catalyst makes the reactant rate go faster, but it doesn't affect the point of equilibrium. So it feels good to come full circle and really understand how kinetics and equilibrium are two languages that are trying to discuss the same thing. So at the end of the video, I want to add in one more thing. I want to give an example of a catalyst so you know what it might look like in real life, because my PhD research was about catalysis, and it was the catalysis of something called the water splitting reaction. So here is Rachel's PhD research about catalysis in 5 minutes or less. So my PhD research was about a reaction called the water splitting reaction, which is taking water and splitting it into its individual pieces. And that's a reaction that we use to produce hydrogen fuel, which you've probably heard about in energy discussions as the potentially revolutionary technology that just isn't quite ready yet. So that reaction looks like this. So it's about taking water molecules and splitting it up into hydrogen gas and oxygen gas. So the hydrogen gas can be used as a clean fuel. Meaning it doesn't use any fossil fuels and it doesn't produce any greenhouse gases. Which is awesome. We love that. And so we would really like to be able to use this technology because we're really trying to cut down on fossil fuel usage. However, we know one thing about this reaction. We know its standard delta G value is going to be a positive number. It's positive 237 kilojoules per mole. And we know that if the delta G is greater than 0, this is going to be a non-spontaneous reaction. And non-spontaneous reactions are not going to happen by themselves and are not super profitable. So we need to get our energy from somewhere, but we said we didn't want to use fossil fuels. So one place we can get the energy is from the sun. Because the sun is a free, unlimited source of energy. Great, problem solved. Here's the energy we need to make it run. It's free and unlimited, and we can push that into hydrogen fuel, and it doesn't use fossil fuels. But the problem is, even if we can find the energy to fix this non-spontaneity, this reaction is slow. And slow reactions don't make very much money in industry, and they're not very cheap to run. And if it's not very cheap to run, it will never be cheaper than fossil fuels, because fossil fuels are really great. They're energy dense, they're liquid at all temperatures, and everybody already has cars that are designed to use them. So the only way we're going to be able to ship the hydrogen fuel is if it's cheaper, and if it's cheaper, it needs to be fast. So the kinetics are very slow, and the activation energy is very large. So to improve this reaction, we need to use a catalyst. If we could improve the kinetics of this reaction, it might just be profitable enough to compete with fossil fuels. So let's look at this reaction a little more closely. So we didn't talk about the redox chapter, but if we had, we would have talked about splitting a reaction into oxidation and reduction half reactions. So since we don't know how to do that, we can just say, there is a mechanism for this. And that mechanism has two steps. The first step is breaking up the water into oxygen and protons. And just to be complete, it also produces electrons, see electrochemistry. And in the second step, we take those protons and those electrons, and we use it to make hydrogen gas. So we can use our mechanism skills from the previous section to verify. There's our overall. If we add this together, we can see that the hydrogen ions go away and the electrons go away, and we're just left with 2H2O2 goes to O2 and 2H2. So this is a valid mechanism, and if we wanted to catalyze this reaction, it'll look a little bit like this. So you'll notice that water is a liquid, so all of this would be happening in a liquid, and hydrogen and oxygen are gas. And so one way we can use a catalyst is to provide a place for the molecules to attach while these different reactions are happening. The catalyst is like a docking location. So one of the things that I did in my research was I made catalyst particles, and they had little extra spots on them that were called co-catalyst particles. And these catalysts were docking zones for each of the different steps of the mechanism. So there was one type of co-catalyst. There was a docking zone for the first step. And there was a second type of co-catalyst that was a docking zone for the second step, a place where the hydrogen ions could combine together to form hydrogen gas. And the catalyst was also the one that absorbed the energy from light. There's a little lightning bolt there. And as you notice, the electrons are kind of like an intermediate in this reaction. They're produced in the first step and they're used up in the second step. So they're produced by the reaction in step 1, and then they need to travel over to step 2. So the catalyst is also a way to transfer these electrons from one step to the next. How to transfer it in space. So I hope you have enjoyed this real-life example of what catalysis looks like in a PhD research setting and why it is important to improve the kinetics of a reaction for industry and economy and real life. And this is the end of the kinetics chapter.